Let's once again let T be a lifetime of an appliance, a refrigerator, say. T is a random variable. Notice I'm using a capital letter. It's important to use capital letters for random variable names because we're also going to use little letters, like a little t, for ordinary variables related to the random variable. The random variable is more abstract of an idea than the regular variable. The regular variable represents numbers and variables in the ways we usually think about them. That's representing the random lifetime. Whenever you see such a thing, you want to remind yourself that it's got a PDF, a probability density function, and a CDF, a cumulative distribution function. We're going to label the PDF little f of t and the CDF capital F of t for good reason, because capital F will be an antiderivative of little f. The derivative, capital F prime, will equal little f. You can find f capital F by integration. You can find little f by differentiation. It's good to have both formulas. Unlike what we did on Monday, for the present value random variable, I'm going to use a different letter that's more consistent with what actuaries do. On Monday, I used the letter P because it represented a present value, but I also used PR for probability to distinguish between the two. Today, let's be more consistent with what actuaries do and use the letter capital Z for the present value random variable. This is confusing for people in statistics, however, because in ordinary statistics class, Z almost always represents a standard normal random variable. Almost always. But here it does not. It's going to be the present value random variable. It's going to be a function of t. I could give the function a name. Go ahead and call it h of t, though I may not in general refer back to the letter h. All I'm trying to say here is it's a function of t. And the function in this case, if we are consistent with what we did on Monday, is 1,000 e to the negative 0.04 times t. Always remind yourself what this represents. For a refrigerator that lasts capital T years, this is the present value of the $1,000 warranty payment that you pay to the customer when the refrigerator fails, when it dies. $1,000 is paid at time capital T at continuous interest rate 4% per year by multiplying 1,000 by e to the negative 0.04 times t. This is giving us a number smaller than 1,000. Present value of that future payment. What would you have to deposit right now at a continuous 4% interest rate to have $1,000 in the account at time capital T? It's good to remind yourself what this means. And we're going to try to be consistent with these things. This has got to have a PDF and a CDF as well. It's a random variable, but the PDF and CDF are going to be different. On Monday, I used the letter little f sub capital P and capital F sub capital P. Let's just use a different letter altogether. Let's call it G. Little g of t and capital G of t. If I know, here's the question. If I know little f and or capital F, can I figure out little g and capital G? And the answer is yes, you can. I'm going to do this in the abstract today, not specifying what little f is or capital F, but then we will apply the abstract derivation to some particular examples of distributions for capital T, different examples for its PDF. We will do the exponential decay like we did on Monday. We'll also do a uniform distribution whose graph is really a horizontal line over some finite interval instead of an infinite interval. And if we have time, I'm going to maybe see if we can fit in what you might call a triangular distribution whose graph looks like a triangle, at least if you draw the line here. We'll see if we can fit that in. We use something called the CDF method. CDF method for finding the distribution of Z. In other words, for finding its PDF and CDF. By finding its CDF first, that's why it's called the CDF method, and then differentiating it, take the derivative of it to find the PDF. So we're going to find capital G first. Oh, and I should have done something different up here. Sorry, scratch this out. I should have used Z for the variable name here. So this is little g of Z and capital G of Z. Notice these letters over here are capital letters. The variable names, the T and the Z over here, are lowercase letters. It's important conceptually to keep those distinct. So how does the CDF method go? What is capital G of little z? That's going to be the CDF of capital Z. In probability, a CDF, a cumulative distribution function, is always, in all circumstances, the probability that the random variable is less than or equal to the given number. Here I'm going back to using P for probability instead of PR. This is always what the CDF is, no matter what the situation is. We are only considering what are called continuous random variables that take on values, all possible values on an interval on the number line, a continuum. There are also discrete random variables that might take on only finitely many values. For example, if you roll a six-sided die, you're going to get a 1, 2, 3, 4, 5, or 6. A discrete number of values, a finite number of values, could be what's called countably infinite as well. You might roll the die until you get a 6, and that could take a really, really long time in theory. That's discrete as well. But our variable here, Z, can take on any value, really between 0 and 1,000. T can take on any positive value if we allow it to be an exponential decay for the distribution of capital T. But Z has to be less than or equal to 1,000 and not negative either. Between 0 and 1,000 is the domain really for Z. We find this in the same way we did on Monday. Replace Z with its dependence on T. Z is 1,000, e to the negative 0.04 t. I'm replacing the capital Z with that, but I leave the little z as is. Little z is just a number. It's the same number that it is over there. These got to be the same number. Capital Z is related to capital T as a function of capital T. So I make the replacement there, but I leave that as a little z there. I want to solve this inequality inside the probability symbol for capital T. Why? Because that's going to relate it to the CDF of capital T, because capital F of T by definition is the probability that capital T is less than or equal to little t. We want to use that fact. If we can isolate capital T, on the left here is capital T less than or equal to something perhaps, or greater than or equal to, and then do 1 minus a probability like we did on Monday. We will do that again. We can relate this to the CDF of capital T. So do the algebra now. Divide both sides of the inequality by 1,000. 1,000 is a positive number. Multiplying or dividing both sides of an inequality by a positive number does not change the direction of the inequality. I'm trying to isolate t, so I want to get rid of the e. So I use a logarithm. Take the log of both sides of the inequality. Because the natural log function, ln of x, is an increasing function, it preserves the direction of the inequality. If a is less than b, then ln of a is less than ln of b. So the direction of the inequality is preserved here. When I take the ln of both sides. But now when I isolate t by dividing both sides by negative 0.04, the inequality changes direction, because multiplying or dividing both sides of an inequality by a negative number changes the direction. You can always check that with particular examples if you like. Dividing by negative 0.04 is the same as multiplying both sides by negative 25. So we get this. But that, because it's got a greater than or equal to, is not exact same form as this, because that's got a less than or equal to. So the next step is to use the fact that a probability of something happening is 1 minus the probability of the opposite thing happening. Right? If the probability of snow tomorrow is 0.2, the opposite thing is that it does not snow tomorrow, and the probability of that would be 1 minus 0.2, 0.8. The opposite of this is to switch the inequality around and make it technically a strict less than. That's the opposite of greater than or equal to, is strict less than. However, because the variable is continuous, it's okay to convert that less than to a less than or equal to. Since this is essentially continuity, effectively, intuitively, the chances that t equals negative 25 ln of z over 1,000 exactly is so small we could take it to be 0. From a modeling standpoint, it's exactly 0. That doesn't work with discrete random variables, right? If you're rolling a die, you get a 1 through 6, the probability that you get something less than or equal to 2 is not the same as the probability that you get something greater than or equal to 2, because 2 is included in both events. It'd be the probability that you get something strictly greater than 1 minus that. But with continuous variables, you can do this. And this is good, because now this part is easily relatable to this. The little t is replaced by this thing right there. So in fact, this is, you could say, 1 minus capital F of negative 25 ln of z over 1,000. Can this be simplified? It depends. It depends on what capital F is. We will work through one example by hand, the same exponential distribution as Monday, to see that you can simplify it. This is what g of z, capital G of z, the probability that capital Z is less than or equal to little z is. This is the CDF of capital Z in the abstract. We can use the CDF to find the median. Set this equal to 1/2 and solve for z. That would find the median. Would that be difficult to do? It depends on what capital F is. But to find the mean of capital Z, it's better to integrate the variable times the PDF. So I need the PDF, the little g. Just differentiate. Little g of z is the derivative of capital G of z. So I need to differentiate with respect to z, this entire thing right here. The 1, of course, differentiates to 0. Negative capital F differentiates to negative little f. Right? We were assuming capital F was an antiderivative of little f. So its derivative is little f of negative 25 ln of z over 1,000. That input's got to be the same. But then I'm not done because I also need to use the chain rule. I've got an inside function there that's now just a plain old z. So I need to multiply times the derivative of that. Negative 25, careful here. The derivative of ln of x with respect to x is 1 over x. But I have ln of z over 1,000, so I get 1 over z over 1,000 times, use the chain rule again, the derivative of z over 1,000 is 1 over 1,000. When you multiply those fractions, the thousands will cancel. Negative in front of the f times negative 25 is positive 25. F of, this has got to stay as is, negative 25 ln of z over 1,000, all divided by z. That's what I got to get. Crazy, huh? But it's true. This is the right answer. It's important to think about the domain. Domains are important in math. What domain is this formula valid for? I've already mentioned it. Z, what's the formula for z? It's 1,000 e to the negative 0.04 t, where t is a positive number. The biggest this can be is 1,000 when t is 0. T is greater than or equal to 0. As t goes to infinity, this goes to 0. It's exponential decay. The smallest z can be is 0, and the biggest is 1,000. Technically, it can never equal 0 because we're not letting t equal infinity. It could equal 1,000 if t were 0. So I'll put a less than there and a less than or equal to there. It's not a real big deal. Which is which. I should give a caveat. This 0 is what it is as long as t can be arbitrarily large. This is if t can be arbitrarily large. We will consider a model where t is not arbitrarily large. And then, because t can't be as big as possible, z has to be bigger than some positive number as well. We'll do an example like that. But that's what it is if t can be arbitrarily large, with it, like with an exponential decay. All right, let's now use Mathematica to explore this in some pretty powerful ways. Option 1 is going to be the PDF for an exponential decay. It's an exponential distribution, like we talked about on Monday. Lambda is a parameter. Different situations give you different lambdas. We saw on Monday that the mean is 1 over lambda in general. For the sake of concreteness, let's imagine all of our refrigerators. Well, let's imagine we have data on refrigerators. And on average, from the data, they last 10 years. Or very close to 10 years. We could use this model then and take the mean to be 10. In other words, take 1 over lambda to be 10, and then solve for lambda. Lambda would be 1/10 or 0.1 if we do that. Then we could use that value of lambda to do simulation to help us figure out the distribution of z, both with simulation and with theory. And that could help us figure out how much money we need to save now at a 4% interest rate to be able to cover the warranty payments. So again, for confirmation, there's the formula for the PDF of t. It does integrate to 1. What's the mean? Well, it's 10. What's the variance? Integrate 10 minus the mean squared times the PDF to get the variance. It's 100. And the standard deviation is the square root of that. Exponential distributions, the standard deviation happens to equal the mean. That doesn't usually happen. That's very special for exponential distributions. Most distributions, the standard deviation does not equal the mean. Why should it? Why should the spread be the same as the center of mass? In general, that shouldn't happen. But with exponential distributions, they're kind of special enough that it does. We can use random variate to generate data. So this particular code is going to generate 100 data values, 100 simulated data values for lengths of time. And I'm going to compute the mean of the data set and the standard deviation of the data set as statistical quantities. So Mathematica, when it computes these things, it's not computing integrals. For the mean, it's adding up the numbers and dividing by 100. For the standard deviation, it's doing something else involving a summation as well that I'm not going to say. But these numbers should both be close to 10. Not too far. Do more simulations. Sometimes you'll get numbers that are above 10. Sometimes they'll be less than 10. On average, they're not too far from 10. It's believable that the theoretical mean and standard deviation should be 10 exactly based on these simulations. We can look at the data too. These are lifetimes for various refrigerators in years. Oops, not data, but data T. Yeah. Sometimes you get outliers. This one lasted almost 26 years. But on average, these numbers are close to, they average out close to 10. Standard deviation is 10 as well. Using the 2 standard deviation rule of thumb, 2 standard deviations would be 20. Almost all the data is going to be within 20 standard deviations, or 20 units of the mean, between -10 and +30. You would rarely, if ever, get a number bigger than 30. I mean, it would happen once in a while, but hardly ever would you get a number bigger than 30 in this particular model. If you did, it would be an extreme outlier. What do I have here? What's this line? That's using the natural log function in this way to find the formula for g of z. Remember, in Mathematica, log means natural log. So I am doing 25 times f of -25 ln of z over 1,000 all divided by z. This is going to be the formula for the PDF of z. This is very powerful. There it is. Let's confirm this by hand. Little g of z is 25 little f of -25 ln of z over 1,000 all over z. What is little f? It's lambda, which is 1/10, e to the negative lambda, e to the negative 1/10, times t. But what is t now? I need to replace t with this crazy thing, -25 ln of z over 1,000. 25 over 10 simplifies to 5/2 or 2.5. -1/10 times 25 is also 5/2, positive 5/2. In fact, that can be brought up into the power of the z over 1,000 by a property of logarithms. Then the e and the natural log are inverse functions, so they cancel. You get 5/2 z over 1,000 all to the 5/2. Oops, I forgot something. I forgot my over z here. This is all over z. So we get 5/2. Let's put a times 1,000 to the 5/2 here. And z to the 5/2 over z. You get some cancellation to get z to the 3/2 ultimately. It's like we get 5z to the 3/2 over 2 times 1,000 to the 5/2. Is that what Mathematica got? I believe so. Yes, and if you do 5/2 over 1,000 to the 5/2, you do get what you see right here. It is the same thing. We could do it by hand. Let's find things. Let's find the mean, median, maybe a probability. We probably should confirm that G integrates to 1. T can be arbitrarily large here. We need to do the integral from 0 to 1,000. 1. What's the graph of little g look like? Looks like this. This is a PDF. The area under it is 1. Imagine this is a density function for a thin rod. Higher when z is larger, lower when it's smaller. It's more dense on the right than it is on the left. You should expect the center of mass to be closer to 1,000 than to 0. Center of mass is the mean. What is the mean? About 714. Yes, closer to 1,000 than it is to 0. And the 714 itself has practical importance. If this model is an accurate model for the lifetime, the exponential decay, the present value of the future $1,000 payment on average is going to be 714. For thousands or maybe even millions of customers, you should save that much for every refrigerator right now at 4% to be able to cover all the warranty payments. Or give yourself a little cushion, save more, or find a better interest rate to give yourself a little cushion. We could find a probability. What's the probability that the present value of an arbitrarily chosen refrigerator from one arbitrarily chosen customer will be between 8 and 900? It would be integrate little g from 800 to 900. That probability is close to 20%. Integrate the PDF to find a probability. We've done that a lot before. You could find median. We could use that formula to find the CDF of z and use that then to find the median of z. Set it equal to 1/2 and solve for z. The CDF of t is this. Now use that formula. Capital G is 1 minus capital F of negative 25 ln of z over 1,000. Formula for capital G is this. Set that equal to 1/2, solve for z. It wouldn't be too hard to do by hand. And that is about 758. About half the present values will be bigger than 758, and about half will be less. How is this related to the mean? It's not exactly the same as the mean. The mean was 714. The median is 758. Why is the mean less than the median here? It's because this distribution is left skewed. It's got a long left tail. Once in a while, you get a low outlier. That affects the mean more than the median. It pulls the mean down closer to 0 than the median is. Yes, the mass is closer to 1,000, the bulk of the mass. So the mean is bigger than 500, but it is closer to 0 than the median is because of the long left tail, a left skew to the distribution. I think we're only going to have time for one other option. We'll do option 3 next Wednesday. Option 2, for comparison's sake, let's try this model. Little f of t is 1/20th when t is between 0 and 20, and 0 elsewhere. The graph would be a horizontal line above the interval from 0 to 20, right? Is it okay if I don't draw it? I'm just drawing in the air here. Here's the interval from 0 to 20. You can draw it if you want. Draw a horizontal line with a height of 1/20th. The graph is a rectangle. If you include the sides, base 20, height 1/20th, area 1. It's 0 elsewhere. F of t is 1/20th for t between 0 and 20. It integrates to 1 over the interval from 0 to 20. Why did I pick that? So that the mean is 10, halfway between 0 and 20. It's a uniform distribution. Center of mass is right in the middle. Between 0 and 20, it's halfway, 10. If you integrate t times f of t from 0 to 20, you get 10. Notice these integrals are from 0 to 20, not 0 to infinity. Because the graph of f is 0 when t is bigger than 20. I could compute the variance and standard deviation. The standard deviation does not equal the mean in this case, as is usual. The mean is 10, standard deviation is smaller for this example, 5.8. You don't have the really super high outliers like you won't do once in a while with the exponential distribution. There's less spread. We can do simulation for this, use uniform distribution instead of exponential distribution. The thing that got plugged into exponential distribution was the lambda. What gets plugged into uniform distribution is the interval on which the PDF is positive, 0 to 20. 100 data points, we're going to get a mean and standard deviation of data. Should be close to 10 and 5.8. Keep doing it. You know, typically that will be generally true. There's less spread. You could try applying the 2 standard deviation rule of thumb. 5.8 times 2 is 11.6, round it to 12. Almost all the data is going to be within 12 units of 10, between -2 and +22. Yeah, all of it will be, because it's all got to be between 0 and 20. This formula is once again using this more abstract one right here. Little g of z is 25, little f of -25, ln of z over 1,000, all over z. The formula for little g of z here it's actually simpler than the exponential one. But the domain is trickier. We had to put a 0 there if t can be arbitrarily large. But with this model, t can't be arbitrarily large. It can be as 20 is the biggest it can be. So the integral is not from 0 to infinity. In fact, that would not converge for this function. You have to figure out the smallest possible values of z by figuring out the biggest possible value of t, 20, and plugging into the formula for z. The smallest possible value z is about 449.329. The integral is not from 0 to infinity here, or even 0 to 1,000. It's from 449.329 to 1,000. That's what equals 1. The plot of little g is over the same interval. Notice this is not 0 down here. That's 449.329. It's the area of this graph that's 1. That's a right skewed distribution. It's got a long right tail. Yes, it's more dense near lower values of z. So the mean will be closer to 449.329 than it is to 1,000. Let's see, halfway between 450 and 1,000 is 725. So we should expect a mean less than 725. Is it? Yep, 688. But the mean is more affected by outliers, high outliers in this case, than the median is. We should expect a median that's not quite so big. The median should be less than 688. The CDF for a uniform, since the uniform little f is horizontal, the uniform CDF's got to be a straight line with a positive slope of 1/20th, t over 20. The median is less than 688, 670. I set capital G of z equal to 1/2, solve for z. This is doable by hand as well. The median is less than the mean because the mean is more affected by the once in a while high outliers. You might wonder, why are we getting most of the z values small compared to most being large, when the distribution of lifetimes is uniform for the interval from 0 to 20? You're just as likely for the refrigerator to die in the first year as you are in the last year from time 19 to time 20. So why are most of the z values small? The reason is because the exponential decay from the present value formula affects things more for large values of t than it does for small values of t. It has a larger effect for large values of t than small. That's the intuitive reason why you get more z values that are relatively low. These are present values.